So whenever you're programming, one of the first things you have to figure out is how to store your data, right? Maybe it's a list of high scores or a bunch of usernames, whatever it is. But what happens when you have absolutely no idea how big that list is going to get? Let's dive into why the most common approach can sometimes fall short and explore a much more flexible solution.
Now, your first instinct and the tool most people reach for is an array. They're simple, they're fast, but arrays have one huge catch. They're static. They have a fixed size. You have to decide up front how big it's going to be. And that's where linked lists come into play. They're the complete opposite. They're dynamic and flexible, basically designed to grow and shrink on the fly. So here's our game plan for this explainer. We're going to start by really nailing down why arrays can be a problem. Then we'll introduce the linked list as our solution. We'll break down its most basic part, the building block. Then we'll get our hands dirty with the actual code. And finally, we'll see why this is such a game changer for any programmer to understand.
Okay, so let's tackle that first step. We need to understand the problem we're trying to solve, and it really all comes down to that fixed size issue. And that's the million-dollar question, isn't it? I mean, imagine you're building a to-do list app. How many things is your user going to add? 10, 100, maybe 1,000? If you use an array and you guess too small, your whole program could crash. But if you guess way too big, you're just wasting a ton of your computer's memory. We need a better way, for sure.
And that better way is the singly linked list. Honestly, it's a really elegant solution to this whole problem of storing a bunch of data when you don't know how much you'll have.
So what exactly is it? Well, think of it kind of like a scavenger hunt. A singly linked list is just a chain of items, and we call these items nodes. Each node holds a piece of data, but, and this is the important part, it also holds the address or a pointer that tells you where to find the next node in the chain. So unlike an array where everything's sitting nice and neat side by side in memory, these nodes can be scattered all over the place. The only thing tying them together is that chain of pointers.
And this visual makes it super clear. See, each of these boxes is a node. It's got two parts. The data itself, here it's the numbers 10, 20, and 30, and then that pointer, which is basically just the address for the next node. You follow the arrows, and that last node, it points to null, which is just a universal sign for stop, you've reached the end of the line.
All right, to really get this, we've got to zoom in a little bit. Let's look at that one core component that makes the whole thing work, the node itself. Everything, the whole chain, is built from this one simple piece.
And you know what's so cool is seeing how simple this idea is in actual C++ code. We're just creating a blueprint, a class that we call node. And look inside. It only has two things: an integer called data to hold our value, and a pointer called next. See how the type is node star? That little asterisk is key. It tells C++ that next isn't going to hold a whole node, just the memory address of another node. That's the magic right there. That's what lets us build the chain.
Okay, we've got the blueprint. Now it's time to build something. Let's jump into how we actually use that node blueprint to create our chain, how we add things, take them away, and just look at what we've built. Let's kick things off with one of the fastest things you can do with a linked list, adding a new node right to the very front. If you look at the code, you can see what we do. First, we create a totally new node. Then, we tell its next pointer to point to whatever used to be the first thing in the list, the old head. And for the final step, we just say, hey everyone, this new node is the new head now. Simple as that. Yep, it really just boils down to this easy 3-step recipe. Step 1, make a new node. Step 2, link that new node to the old start of the list. And step 3, update your head to be the new node. It's an incredibly quick and efficient way to add data. But what if we want to tack something on to the end? Well, this is a little different. We can't just magically jump to the last spot. We actually have to start at the very beginning, at the head, and walk the entire list, following that chain of pointers from one node to the next until we finally find that last one that points to null. The logic here has a really important first check. Is the list totally empty? Because if it is, well, our new node just becomes the head. Easy. But if it's not empty, we have to start that scavenger hunt, hopping from node to node until we find the very end. Once we get there, we just change that last node's next pointer so it points to our new node. And just like that, it's part of the chain. You know, just like adding to the front was super fast, taking away from the front is also incredibly efficient. All we have to do is make our main head pointer point to the second node in the list. That effectively just snips the old first node right off. And then, this part is super important, we delete that old node to free up the memory so we don't cause any memory leaks.
So how do we actually see what's in our list? You guessed it, we have to traverse it again. The logic is pretty straightforward. We make a temporary pointer and start it at the head. Then we just start a loop. As long as this temporary pointer isn't null, we print the data of the node it's on, and then we tell it to hop to the next node. We just keep hopping and printing until we hit the end. All right, we've looked at all the individual pieces of the puzzle. Now for the fun part. Let's put it all together and actually watch a full program run using all the functions we just learned about. Okay, here's our main function, our test drive. First, we start an empty list. See how the head pointer is set to null? Then we use our function to insert 10, then 20, then 30 at the end. After that, just for fun, we insert the number 5 at the beginning. We'll print the list to see what it looks like, then we'll delete the first element and print it one more time to see the change. And boom! Here's the result after that first set of commands. Our calls to insert at end built out that main chain, 10, then 20, then 30. Then that insert at beginning call slapped the 5 right on the front, making it the new head. It worked exactly like we thought it would. Our list is built. Next up, we called delete from beginning. And this slide shows you exactly what happened. The node with the 5 in it, it's gone. The main head pointer for the list has been updated, and now it points to the node with 10. That's our new beginning. It worked perfectly. So, we've gone through the nitty-gritty of how to build and manage a linked list. But let's pull back for a second. Why does any of this actually matter? What's the big picture here?
It really comes down to these 3 key things. First, that dynamic size. You never have to guess how much space you need. It just grows and shrinks with your data. Second, certain operations, especially adding and removing from the front of the list, are incredibly fast. And finally, linked lists are foundational. They are the bedrock, the building blocks that are used to create even more powerful data structures, like stacks and queues, that are absolutely essential in computer science.
You know, once you master a concept like this, it opens up a whole new way of thinking about how you program. You're not just storing data in a box anymore. You're building these living, flexible structures. So the real question is, now that you know how to build the chain, what are you going to build with it?